All right, hello everyone. So today we're looking at a calculus 2 problem or problems. You're going to use the ratio test to determine the convergence of the following series. A is series 1 to infinity, quantity 2n plus 7 divided by 3n minus 1, all to the nth power. And for B, n equals 1 to infinity, quantity n plus 1 over n raised to the n squared. And yes, we'll be using the root test here. And the root test, let's just go over that real quick. Basically, you have a series, and you're going to form the limit L, which is the limit as n goes to infinity of the nth root of the absolute value of an. And when you take this limit, and if the limit is less than 1, then the series converges. If it's greater than 1, then the series diverges, and if it's equal to 1, then it's inconclusive. Now, when to use the root test, I think is an important question, because a lot of the time, you have so many tests. The question is, well, which test to use where, what conditions? Typically, I'd like to use the root test when I'm having something raised to the nth power or some version of it, like n here or n squared. That's when it works out really nicely, especially if you have a whole expression raised to the n. And don't get me wrong, if you had something individual like 2 to the n over n to the nth, it might work well there as well. In fact, it would. So, yeah, just keep that in mind when using this test. All right, so let's go ahead and apply it to the first series. So we're going to take the nth root of the absolute value of 2n plus 7 over 3n minus 1, all owed to the n power. Let's go ahead and do that here. So nth root, absolute value, 2n plus 7 over 3n minus 1 to the nth power. Now this quantity, the 2n plus 7 divided by 3n minus 1, that is positive. So I'm going to take the absolute value of that. And then you would have the nth root of n, which would cancel out. Okay, so this is like tantamount to saying like the square root of x squared equals x when x is greater than 0. That's what we're saying. So many words. So we take the limit now of n going to infinity of the quantity left inside, which would be 2n plus 7 over 3n minus 1. And all of that would equal 2/3. Okay. So L is equal to 2/3, which is less than 1. And therefore, by the root test, the series converges. Okay. And yeah, the conditions, if you look at them, they're very similar to the ratio test, in fact. Less than 1, equal to 1, less than 1, greater than 1, equal to 1. So we have all that as well. So it's somewhat easy to remember, in my opinion, in that sense. All right, so for the next series, we have series 1 to infinity, n plus 1 over n to the n squared. We're doing the same thing. Now for this one, computation is a little more involved, so that's why I also wanted to bring that in. And it's, in my opinion, mainly with the limit. So nth root of absolute value of n plus 1 over n to the n squared. Okay, so first of all, this is always a positive expression, the one that's inside the absolute value, so we don't need it. So it's going to equal the limit as n goes to infinity of the nth root of n plus 1 over n to the n squared. So, you might say n squared and n, that doesn't cancel out so easily by just looking at it. Well, another thing you can do is this. You can, in terms of the computation way we can look at it, this is like saying all raised to the 1 over n power. And I could go ahead and rewrite this as n plus 1 over n squared times 1 over n. So I'm using properties of exponents. If you remember, we had one property that said if you have a to the b, all raised to the c power, it's equal to a to the b times c. So that's what I'm using here. And yeah, it's very easy to forget those rules. They come up quite a bit here when you're working with series with exponents and such. And n squared times 1 over n, one of the n's cancels, and you have this. And how do I take this limit now? Well, it's got the form of 1 to the infinity. So you can use like something involving L'Hopital's rule. A little more, it's just not L'Hopital's rule. You have to, I'm not gonna go into this because I don't want this longer than it needs to be, but you can call that y and take the natural log of that. So if you can recall that, please. So you can certainly do that and you get the limit, or you can do the following. Yes, and again, it's 1 over to the infinity, which is an indeterminate form, so that's why we could consider that. But the other way to look at it is this way. If you rewrite that expression, quantity n plus 1 over n to the nth power, it's like saying 1 plus 1 over n, all raised to the nth power, and that's equal to e. Okay, so it's very nice to recognize that limit because it kind of comes up often here. And since e is our limit, it's greater than 1, then the series diverges. So n plus 1 over n squared diverges by the root test. Right, now, I would not use it on things that are not raised to the n, basically because of the fact that like polynomials, logs, etc., because usually your limit's going to be 1, so you'll do a bunch of work just for nothing. So I had mentioned the cases of where you would use it, and I just wanted to mention the case where you wouldn't. Okay, well, thank you for your time. Hope this helped.